Good morning. Let's begin. Last time we had two lectures back to back, 33 and 34. Quite a few new concepts were covered. So today it will be a little bit longer and more detailed review so that we can pick up from there. We are talking broadly about the topic of multi-carrier modulation, and the motivation for multi-carrier modulation stems from the fact that we want to deal with wideband signals. So that is primarily our interest. A wideband signal has several challenges. You get frequency selective fading, and the complexity of the equalizer is quite a challenge. So we said that a wideband signal we will treat as n narrowband carriers n cross b. Okay. So this is where the multi-carrier modulation concept is coming from. So b, the bandwidth of each of the sub carriers or each of the carriers is chosen to handle dispersion. We said that the bandwidth is related to the baud rate determines how sensitive you are to dispersion. So basically I will say that B is chosen, you have to choose it to handle time dispersion. Once you have done that, then the number of channels gets fixed, n denotes the number of carriers, and the number of carriers you need to achieve a certain bandwidth. So basically the key decision in this in the design of a multi-carrier system, one is the choice of the bandwidth B, because that is what is going to tell you how robust your system is going to be. And once you have a multi-carrier system of this type, we said that so we will say that now we have a MCM framework. The wideband signal is now transmitted as multiple narrowband carriers, and in order to achieve capacity in a MCM framework, we will do water filling, and that is where the interest in terms of capacity comes from. And we said that we will do water filling over time and over frequency to achieve the capacity at every time instant, and then at each time instant the channel changes and then you adapt accordingly. So all of this is done to maximize the throughput of your system via CSIT. You need to have channel state information at the transmitter, so which means that there is a feedback channel. So this is the framework of the multi-carrier system. Now where does Multirate DSP play a role, and what is the benefits that we can get is what we are going to be what we focused on. So we have this notion of a transmultiplexer. Transmultiplexer is a device that converts from narrowband signals to a wideband signal. Now when we did the design of the transmultiplexer, what we talked about in the ideal case where these signals were side by side without any gaps, that is what we refer to as a minimal system. It occupies the minimal bandwidth that is required. On the other hand, if you want to have practical filters, we would have to introduce some guard bands so that you can have the filtering, and this is where the notion of redundancy has come in, and we were leveraging this in the last lecture. Okay. Now redundancy, along with that comes the notion of orthogonality. Basically we want to be able to establish these signals independent of each other, these narrowband signals. So we are looking for ways of separating them. Of course separating them in frequency is one way, and there are other ways by which you can say that okay, you do not have to, as long as they do not overlap, there is a notion of orthogonality in frequency, I should be able to separate. But from a practical standpoint we said okay, that is not possible, you would have to allow some overlap because you cannot have perfect filters. The challenge is how do we design with overlap, still maintaining orthogonality and maintaining something that is close to a minimal system. We made an observation that the IDFT DFT gives us one such framework, maybe just the mathematical or the thing that go with this figure. So let's take the IDFT matrix. So basically it is W inverse. If I were to ask you to write down the IDFT matrix, this would be 1 over n times the conjugate of the DFT matrix. The conjugate of the DFT matrix is Wn Kn, this will be Wn minus Kn. and DFT matrix is symmetric. So, it's strictly you would have written it as minus nk, but it is the same. So, what does this actually come out to be? It is 1 over n e power j 2 pi over n times k n. Okay. K represents the harmonics 0, 1 to n minus 1. So, you can think of these as the harmonics of the fundamental frequency e power j 2 pi over n, they are the harmonics, and you are looking over a time window which has n samples, okay, am I doing n or n? N, okay, so you are looking at n samples, okay, this is your notion of the time space. So, given this, each of the rows are orthogonal, though they overlap in frequency. So, that is the figure that we have, they are overlapping in frequency, nevertheless you have a system that is orthogonal. So, the IDFT is a very powerful concept that we bring from DSP and say, oh, by the way, we have a framework that already satisfies whatever the system you are looking for. You want to have orthogonality? Yes, we have. You want to have minimal bandwidth? We can do minimal bandwidth. Overlap is needed? Yes, overlap is present, but we still have orthogonality. Okay, so that is one piece that we will leverage a lot. We also reviewed the blocking and unblocking operations. The blocking operation, the creation of blocks, happens through a advanced chain by downsampling. We call this as the blocking, the inverse or the reverse operation as the unblocking operation with the delay chain. And we said that using the result of upsampling followed by a delay followed by downsampling, there are certain simple simplifications that we can achieve. If you did not have this z power minus 2, these would be straight lines. If you have a parallel to serial and a serial to parallel converter, but if you had delays, then you start to see some changes in the interconnections. But again, this is a very simple example, but the more important thing is what happens when we have it in the context of a practical channel. Okay. So, we also mentioned that we have two types of polyphase decomposition. Type 1 associated with when there is a delay chain, type 2 associated with the structure that has got advanced operators. So, just a quick definition, type 1 you have powers of z power minus k, that is the delay chain, series of sequence of delays. The type 2 has a series of advanced operators. So, again type 1, type 2 was reviewed. Now, notion of redundancy, we have already said that a minimal configuration would require them to be sort of packed tightly. When you have a little bit more of a gap, you would have more spaces. Now, how do you visually achieve that, or intuitively achieve that? You are here in this particular, in the minimal system, there are m signals, I upsample each of the signals by m. So, the sampling rate is maintained. Now, maybe we can write this down a little bit more formally. Let me just create a box which we can fill in with some information that, so the notion of redundancy is what we are trying to capture here. Redundancy says in this case there is additional resources being utilized, but how do I achieve? So, if I have a minimal transmultiplexer, okay, so which means that I will go from a TDM system to a FDM system. FDM is the wideband system. Okay. So, this is m parallel signals and this is a wideband signal. Okay. So, this is the wideband. So, the minimal system says that if I have a sampling rate ns per signal, ns samples per second for each signal, then I have m of them. So, the total is m times ns. Okay. Now, that is what the parallel branches give you, right. When you have a, where is the parallel branches have m branches of them. Now, on this side, So, if each of these is ns and you have m of them, and because of the upsampling this becomes m times ns, right. So, that is a minimal transmultiplexer. So, minimal transmultiplexer is one where you have, but if you did upsampling by n, so with redundancy, we are increasing the number of resources. So, it is n times ns where n is greater than m. So, somewhere the notion of additional resources comes in. The minute you have a higher sampling rate, you know that more bandwidth is being used, which means that if you still have only m signals, obviously there is some gaps which are present. Again, may not be exactly as you visualize it, but the notion of redundancy and how it's introduced into the system was an important element from the last lecture. Okay. So, with this configuration, we said how will the synthesis filter bank look, because that is the first stage of the transmultiplexer. Upsampling by m followed by the filter, that is a minimal configuration, but we introduce upsampling by n with the same filters, but now these filters have to be slightly differently designed, but that part it will come later. So, the vector representation is a scalar f naught f1 up to fm minus 1 multiplied by these signals which are upsampled. So, basically we get a combining of the signals, that is why it is called the synthesis filter. We wrote down the time domain expression, that is more for completeness, but the one that we wanted to focus on is doing the polyphase decomposition. Once we did the polyphase decomposition, we showed that the the synthesis filter bank can then be represented in this form, where G of Z is a rectangular matrix. You are splitting each filter into n polyphase components, there are m of them. So, basically the polyphase components of each filter are along the columns, and there are m such filters, and therefore you get an n cross m. Basically it is the redundancy part is being shown by a trapezoid instead of a rectangle. Similarly, you can introduce, so basically you can move the using the noble identities. So, this is how. Okay. Now, analysis filter bank, we said we will do a type 2 polyphase decomposition. So, basically this is the structure of the polyphase analysis filters. Since you have upsampled by n, which means the introduction of redundancy, you must downsample by n in order to remove the redundancy, because at the end of the day you want to have the original signal back. So, basically we are doing the downsampling by n, following the same procedure, doing polyphase decomposition, and then the noble identity, we get the following structure. Okay. So, I am assuming this part of it you are able to review and are comfortable with that. Then we went to the putting the entire transmultiplexer together. So, the synthesis portion, the analysis portion with the channel in between. Channel has got the dispersive channel as well as the noise. We said that the noise we will more or less ignore, because that is it comes as an impairment which we cannot do anything about, but the channel impairment we definitely want to address. So, given this structure, we then went back and said that there is a understanding of what can happen in the channel. You can have mixing of the signals, that is called inter subchannel interference, and then you can have intersymbol interference within each subchannel, that is called intra subchannel interference. So, basically two types of distortion, both of which need to be eliminated for us to get a uniform detector. So, there is a result that we introduced along with the notion. The result is known, notation is new, but we introduced it. Upsampling by a factor of m, followed by a filter, followed by downsampling by a factor of m. We said that this is LTI, important. This is an LTI system, and its transfer function is equal to the 0th polyphase component. And how did we represent the LTI system? We represented the LTI system in terms of h of z, that is the matrix, the transfer function with the down arrow, which basically means that you will downsample this by a factor of m. You downsample h of z, what will happen? You will get you take the impulse response and downsample it. You will be left with the polyphase component 0, and all the other things are thrown away. So, basically what you get is E of z. So, this is an important result. Please keep this notation reference handy because that is what helps us simplify the figures that we have in the next chart. Okay. So, now if you labeling of the signals very important, let me just make sure you have S0 to Sm minus 1 on this side, okay, U0, U1, Um minus 1 on this side, okay, and S hat, S1 hat, Sn minus 1 hat. So, I am looking at the transfer functions between S0 and S0 hat. So, if you basically look across from one end to the other, okay, M can be from any one of these and K can be any one of those. There is always going to be an upsampling by N, a filter, the channel, keep in mind I am ignoring the noise, another filter, downsampling by N and the output. That is what is going to be the chain between input and output. So, we know that this configuration can be simplified, and we know that that is going to give us an LTI system, and the transfer function of the LTI system is given by Hk followed by Ck, C of Z followed by Fm downsampled by N. So, given this, we could then write down a matrix transfer function between the whole set of inputs and the whole set of outputs, and we related the properties of T of Z to the two types of interference, whether it could be interblock, intra-block. Both of these we described saying, okay, if you get a diagonal, there is no interblock there is no interchannel mixing. If you get each of these matrices to be a constant matrix, then there is no interblock interference, and I think both of them are very important. So, basically this is the matrix. This is how you could write it is a polynomial of matrices, and then we indicated that if this matrix turns out to be a constant matrix, there is no interblock interference, and if it is a diagonal matrix, then it becomes no interblock, no intra-block interference. So, this is not inter, this is intra. Okay, this should be intra-block. Okay. So, no, it is inter. Sorry about that. Actually, this is inter only, I am sorry. Okay. Last review portion of this thing is that we wrote down the polyphase implementation, the matrix representation of the synthesis filters. These are the synthesis filters followed by the analysis filters. Okay. Very important. Once we have this, we obtained the representation in terms of the polyphase components of these matrices, and we also said that we will write C of Z in terms of its own polyphase decomposition, and then we obtained a transfer function between R's. R's are the input to the S matrix, and X's x0 x to n minus 1 are the outputs of the G matrix. So, between these two matrices, between the two green sets of green lines, we got this transfer function, and we showed that it was a pseudo circulant. Okay. So, this is pretty much where we are in terms of the overall understanding and overall representation.